Imagine for a moment your most sensitive digital information. It could be anything, really banking details, private messages, maybe company secrets, even critical infrastructure data. We instinctively trust encryption, right? To be this digital fortress guarding it all, the ultimate lock. But what if that trust is subtly undermined? Not by brute force, not guessing the code, but by simply listening to its whispers, the faint echoes it leaves in the physical world.
Today, we're embarking on a really fascinating deep dive. We're looking at where digital security crashes right into physical reality, the hardware itself. We're going to explore how tiny, almost imperceptible side channels, these unintended leakages, can give away secrets from even the strongest encryption. And, just as importantly, we'll uncover the ingenious ways engineers are fighting back, designing defenses that are not just stronger, but, well, smarter, more adaptive.
That's spot on. And it's exactly what makes the research we're diving into today so compelling. It's work from Purdue University and Intel Corporation. The title is quite a mouthful. A digital cast-coded signature attenuation countermeasure with intelligent malicious voltage drop attack detector for Empower SCA Resilient Parallel AES 256. But don't let the title intimidate you. The core idea here is incredibly insightful and frankly vital for our digital safety. It gets right down to how even computationally secure cryptographic algorithms like AES 256, the gold standard we rely on, can still be vulnerable. Not through math flaws, but through these things called side channel attacks. It's really about rethinking where the weaknesses are,
Yeah.
down to the silicon level.
Okay, let's unpack this. Our mission for this deep dive then. First, let's demystify side channel attacks. How do these invisible footprints happen? How do attackers use them? Second, we'll look at the defenses. What's been tried, what worked, what didn't, kind of the history there. And finally, we'll zero in on this groundbreaking new defense mechanism the researchers developed. It's not just a stronger lock, it's a lock that knows when it's being picked in a weird new way, and it reacts. By the end, you'll really understand the subtle, high-stakes dance between secure design and sophisticated cyber threats. It's a battle fought at the microscopic level, and it matters a lot. So let's start by defining this hidden threat. Most of us think encryption is purely math, right? Abstract code, prime numbers, impenetrable digital locks, and well, that's true to a point. But the key thing often missed is that these algorithms don't just float in the ether. They run on physical hardware, on the tiny silicon chips inside your phone, your computer, everywhere. And that physical hardware, like anything real, leaves traces, like footsteps in a room.
Exactly. Think of a detective at a crime scene. Maybe the main event is over, the data is transferred. But the room itself, it's full of tiny clues. Footprints, smudges, maybe faint sounds lingered. Analyze those clues carefully, and you can piece together what happened. That's basically what a side channel attack does to a crypto chip. Attackers are looking for this side channel information. Tiny, almost imperceptible things, like the exact fluctuations in power consumption as the chip encrypts something, or the tiny electromagnetic, or EM, emissions it gives off. Every time a transistor switches, every time a bit is processed, there's a little ripple, a physical signature. And it varies just slightly depending on the data being handled and the operation being performed. Which, well, it raises a really important question. How can these sophisticated digital systems leave such physical clues? Well, let's try an analogy. Think of a car engine. Idling, it uses a certain amount of fuel, makes a steady hum. But accelerate hard, go uphill, it uses more fuel, the sound changes, it roars, maybe whines. A crypto chip is, surprisingly, quite similar.
Processing a 0 might draw slightly less power or emit a slightly different EM signature than processing a 1. Or, more importantly, when it does a specific math operation, say an XOR on part of the secret key, that operation has a unique physical fingerprint, its power draw, its EM pattern. Now, these variations aren't flaws in the algorithm's math. The math is solid. The vulnerability is purely in its physical implementation, how it runs on the silicon. So an attacker, by measuring these subtle changes power, EM over and over again millions of times, they can start to correlate those physical events to the chip's internal operations. Using advanced statistics, they gradually piece together enough information to pull out confidential data, usually the most critical thing, the secret encryption key. And they do this without ever breaking the algorithm mathematically. It's like a safecracker listening to the clicks, not guessing the combo. So just to really nail this down, the core concept, side channel attacks, SCA, they don't attack the math, they exploit the physical implementation. We're focusing mainly on PowerM side channel attacks here, because that's what this Purdue and Intel paper tackles head on.
The crucial takeaway for you, our listener, is that even super strong algorithms like AES 256, ones considered computationally secure, are susceptible if they aren't properly protected at the circuit level, where the electrons actually flow, and the attacker's goal. It's almost always to extract that confidential data, specifically the secret key. They use techniques like correlational power attack, CPA, or correlational EM attack, CIMA, to find those tiny telltale correlations.
Okay, CPA and SEMA correlational power or EM attacks. Conceptually, how do they work? It sounds incredibly difficult reconstructing a key from faint electrical noise.
Oh, it is. It really is a feat. But think of it like this. Imagine trying to guess what word someone is typing just by listening to the unique sound each key makes. If A always made a slightly louder, higher click than B, over time, recording millions of those clicks, analyzing them, you could start to infer the words, right? Well, with crypto chips, attackers use sophisticated statistics to find those tiny predictable clicks, the unique power spikes or EM pulses that happen consistently when the specific part of the secret key is being used. They run the encryption millions of times, measuring the side channel trace each time. Then, they make guesses, hypotheses about what the secret key might be. For each guess, they calculate what the power trace should look like, theoretically. Then they compare that theoretical trace to the actual traces they measured. The key guess whose theoretical trace shows the strongest statistical correlation with the real measurements. That's very likely the correct key, or at least part of it. It's all about finding that needle in a massive haystack of noise, because you know exactly what shape the needle should have.
Right. So clearly, this isn't some brand new problem security engineers just discovered. They've known about these invisible footprints, these side channel attacks, for a while, and they've been actively working on solutions, evolving the designs. These are like early attempts to sort of mask those digital footsteps, make the detective's job harder.
It's exactly. For years, engineers have developed various circuit-level countermeasures, specifically for power and EM SCA. And it's led to some really clever techniques, each a step forward, but each with its own pros and cons. Like in the early days, you saw things like the current equalizer. The basic idea was simple. If the attacker looks for variations in current, let's try to make the current draw as constant as possible. So it dynamically adjusts things to smooth out those fluctuations, trying to hide the key-dependent patterns. A good first thought, but often not quite strong enough against better statistical attacks. Then other methods came along. Things like the series LDO with randomization. LDO is a low dropout regulator, a type of power regulator. Adding randomization was the key idea there. Introduced some unpredictability into the power delivery, hoping to scramble the side channel signals, made them harder to correlate back to the key. There was also the integrated buck regulator, IBR, another way to try and stabilize the power supply voltage, reduce those telltale fluctuations. These early methods were important steps, definitely. But the paper describes them as offering, well, moderate security, achieving around 10 minimum traces to disclosure, or MTD.
Okay, MTD, minimum traces to disclosure. That sounds important. What does 10 million traces actually mean for an attacker in practice?
MTD is absolutely central here. It basically tells you, our listener, how many times an attacker needs to watch the encryption happen, how many side channel measurements they need to collect before they can reliably figure out the secret key. So 10M means 10 million encryption operations. Now, 10 million sounds huge, right? But for a modern attacker with specialized lab gear, they can collect millions of traces surprisingly fast. Maybe minutes, maybe hours. So moderate security at 10 MTD, well, way better than zero protection, it's often not enough to stop a determined, well-equipped adversary for very long. Right. So the field pushed forward towards more advanced techniques, especially focusing on signature attenuation. The goal here isn't just stabilizing power, but actively suppressing or attenuating that specific key-dependent signal the attacker wants, like filtering out one specific radio frequency. A big leap came with current domain signature attenuation, or CDSA. This is an analog technique, and it achieved much better security over 1B MTD. That's a billion traces, with just one method. That was a real game changer, showing really high attenuation was possible. Other complex approaches also popped up, like a randomized nonlinear LDO cascaded with arithmetic countermeasure. Cascading just means combining different techniques. This achieved similar high security, but needing two methods made it more complex. Later, a process-scalable version of that analog CDSA was developed. Without something called bleed-RO randomization, it got about 20 MTD, respectable but not amazing. With that randomization turned on, though, it could hit 250 MTD. And if you cascaded that with another technique called TVTF, time-varying transistor flow, well, that provided the highest security till date, before the research we're talking about now. So you can really see this constant arms race, right? Engineers always pushing for higher and higher MPD numbers. But despite all these advances, these existing solutions have their own issues, significant trade-offs. For instance, the paper points out that digital-friendly NLDLDO suffers from higher overhead. What does that mean? Well, digital-friendly techniques are usually preferred in modern chip design. They integrate better with automated design tools, manufacturing processes. But these specific ones, while easier to implement in some ways, often cost more in other ways. They might use more power or take up more physical chip space. That's the higher overhead. That could be a deal breaker for, say, battery-powered devices or low-cost gadgets. Another big issue, an arithmetic countermeasure. While it was fully synthesizable, meaning software could design and optimize it automatically, which designers love it, was also algorithm specific. That's a major drawback because it cannot be easily ported to another encryption algorithm. Imagine crafting this incredibly intricate custom lock for just one specific door. If you need to secure a different door, even slightly different, you have to design a whole new custom lock. Not efficient, not scalable for a world using lots of different crypto. And finally, while some digital-friendly current sources, CS, did manage to bring signature attenuation into the digital world, they generally lack the high attenuation and MTD from analog cascode CS seen in the earlier analog work. There was this definite performance gap, a desire to get that really strong analog security but using more modern digital-friendly circuits.
So what we're seeing is this history of innovation, definitely, but also a series of tough trade-offs. Solutions were effective, sure, but maybe too complex or too specific to one algorithm, or just not quite as powerful when implemented digitally compared to their analog cousins. It really sounds like there was a gap, yeah, an area where things could be significantly improved. The challenge was blending that top-tier security with practical digital design needs. And this, dear listener, this brings us right to the heart of today's deep dive. The researchers at Purdue and Intel, they didn't just look at the existing stuff and try to make tiny improvements. They saw not just a gap, but a crucial, largely unexplored area in this ongoing battle. They saw a next-generation threat that the current best defenses weren't even designed to handle.
That really raises the key question for any security researcher, doesn't it? What's missing? What's the next vulnerability in the state of the art? And the paper highlights several really important motivations for their work. First, and this is huge, they identified a major blind spot. Most importantly, a dedicated attack on the state-of-the-art, so A countermeasures, is still left unexplored, end quote. That's critical. If you don't understand how your best defenses might be subtly bypassed, you can't really protect against future attacks. Attackers are always innovating. Security has to be proactive, not just building walls, but anticipating how someone might cleverly get around them. Second, and this is where the intelligent part of their research title really comes in, this work for the first time explores the possibility of an attack on signature attenuation hardwares using malicious reduction of voltage and utilizes an intelligent attack detector circuit to detect such attacks and adapt to it, to guarantee the efficacy of such signature attenuation-based countermeasures. This is a massive leap, moving from static, passive defenses to adaptive, self-aware security.
It's like instead of just having a strong lock, you have a lock that senses if someone's trying to subtly weaken its internal mechanism, and then it actively responds. It changes the game from fixed defense to dynamic defense. And finally, beyond just anticipating new attacks, they also aimed for a direct, substantial improvement on existing digital techniques. They wanted an improved digital-friendly cascoded CS, achieving the highest signature attenuation with digital-friendly technique till date, i.e. a 10x improvement without RO bleed randomization. So they weren't just thinking about new theoretical attacks. They were simultaneously making the existing digital defense stronger and more practical. The goal was to get that analog-level security, but within a purely digital-friendly, scalable framework.
So the ambition here was pretty wide-ranging and impressive. Not just build a better wall against known attacks, but build a wall with smart sensors. Sensors that can spot new kinds of breaches and react instantly, dynamically. It really feels like a philosophical shift, doesn't it? From passive defense to active, adaptive security right there on the hardware, ready for whatever attackers think of next. Okay, here's where it gets really interesting. This ambitious goal led them to develop something called the Intelligent Digital Cascoded Signature Attenuation Circuit, or IDCSC. Yeah, it's a mouthful, we know. But the concept behind it is genuinely brilliant, a major step forward in hardware security. Not just tweaking things, but a fundamentally smarter way to defend.
Absolutely. They architected this solution, the IDCES, and built it into a physical test chip. Using a 65-nanometer CMOS process, let's quickly break that down. 65 millimeter is the manufacturing tech feature size, how small the transistors are. Smaller means more packed onto a chip, usually better performance, lower power. CMOS is complementary metal oxide semiconductor. It's the standard tech for making most chips today because it's pretty power efficient. By putting the IDCES right alongside a parallel AES-256 encryption engine on this test chip, They could see how well it worked in a real crypto context. Now, the IDCSE itself, it's made of several clever parts working together. The real heart of the attenuation is the digital cascoded current source, or DCCS. This is what actively suppresses those key-dependent current wiggles attackers love. And it's not just one big current source, it's made of 32 CS slices. Think of each slice as a tiny, precisely controlled tap for electrical current. Each slice uses 2 PMOS transistors. POS is just a type of transistor, a basic building block, and here they're biased to operate in the saturation region. Okay, saturation region. What's that? Imagine a garden hose.
Turn it just slightly on, the flow is really sensitive to small knob twists, but open it almost fully. Water flows steadily, powerfully, not much affected by tiny adjustments. Saturation is like that steady, powerful flow for a transistor. It's the most stable point for delivering a consistent current, and that stability is key for masking those power fluctuations. When it's in saturation, it acts like a really good constant current source, provides high attenuation. Similar to those robust analog current sources from earlier research, but done digitally. And how did it keep it in saturation? Well, the top PMOS transistor in each slice is biased by multi-stage, parallel, self-biased NAND gates. This is pretty clever. These aren't just logic gates, they're configured to automatically adjust the control voltage for that top PMOS. This self-biased tunability is crucial. It lets the current source adapt, stay in that ideal saturation region, even if conditions change slightly. The bias voltage can be tuned from 0.5 VDD to VDD. VDD is the main chip voltage. The bottom POS is simpler, biased by a self-biased NOT gate, giving a fixed 0.5 VDD. This whole cascaded setup, one PMOS on top of another, precisely biased, is what gives it such strong attenuation.
Okay, so if I'm getting this right, these components are working together like a super sophisticated self-tuning noise-canceling system for the power, smoothing out the electrical noise that carries the secret key info, not just static, but constantly adjusting itself.
That's a great way to put it. It is indeed self-tuning. And beyond the DCCS, there's another piece. Ring oscillators, RO as a bleed path. These aren't just any ROs. They're multiple scan-controlled parallel ring oscillators. And they do two key things. First, they bypass the delta changes in the supply current. So if the main power line has tiny, rapid fluctuations carrying secret info, these ROs act like a shunt, absorbing and smoothing those out before they get seen outside. Second, they stabilize the VAES node voltage by providing local negative feedback. This keeps the voltage right at the AES engine itself very stable, which is crucial, not just for AES to work right, but also for hiding those small, key-dependent current changes that attackers look for. And finally, there's a global feedback loop, managed by a switch mode controller, or SMC. This is a slow loop, reacting to longer-term changes compared to the fast RO bleed action. Its main job, to compensate for TVT variation. That's process, voltage, temperature variations, unavoidable things in chip-making, power supplies, environment.
The SMC also handles sudden changes in the crypto current due to frequency variation of the encryption engine. So the ROs handle the fast, local noise. The SMC handles the slower, broader drifts. Together, they keep the whole system incredibly stable and secure across different real-world conditions.
Wow, okay, putting it all together. It's like trying to eavesdrop on a room, but there are multiple layers of advanced filters. First, a self-tuning system masks the speaker's voice variations with a steady hum. Then, another system keeps the room's acoustics perfectly stable, absorbing any outside noise like air conditioning kicking on. It's incredibly layered. And this IDC-SD design achieves a signature attenuation of 343x in simulations. So what does this all mean for us, the listeners, in practical security terms? Well, that 343x attenuation translates into a projected expected MTD increase of 3,432 or 100,000x compared to unprotected AES. That's just a massive, almost unbelievable leap. It makes it vastly harder, maybe practically impossible for attackers to gather enough traces to get the key, turning those whispers way, way down. And there's always a but in cybersecurity, isn't there? The researchers didn't stop there. They didn't just build a better defense. They wisely anticipated that attackers don't stand still. They get smarter. They find new angles. So they proactively thought about what a truly intelligent attacker might try next to get around even this strong countermeasure.
Exactly. The paper introduces a really novel and, frankly, quite worrying attack idea, the malicious voltage drop attack. This isn't your standard brute force, nor is it just passively listening like traditional SCA. It's a precision strike, specifically designed to undermine signature attenuation hardwares, like their own IDCSC. It exploits a fundamental property of how these current sources work to achieve high suppression. Remember how we said high suppression happens when the current source, the CS, is in that stable saturation mode? Well, an intelligent attacker, knowing this, would aim to secretly push the CS out of saturation and into its linear region. In the linear region, the current source's ability to attenuate the signature drops significantly, becomes much more transparent to side-channel snooping. It's like finding a way to make that steady hose stream suddenly turbulent and revealing again. Now, the attack mechanism itself is quite clever. The attacker subtly reduces VDD from the desired value. VDD is the main chip voltage, but they do it very carefully, very covertly. Crucially, they make sure the lower threshold and upper threshold of the global SMC loop remain constant. Remember the SMC, that slow feedback loop keeping AES running smoothly. If the main voltage drops just a bit, the SMC's programmed response is to compensate. It turns on more CS slices to draw the same amount of current overall, keeping the AES engine happy. The chip thinks everything's normal. But here's the killer flaw they exploit. Even though the total current is the same, because the overall VDD supply voltage was secretly lowered, some of those individual current source slices get pushed out of saturation into that less effective linear region. And when the CS is in the linear region, signature attenuation will be reduced. Critically, this increases the correlated power aiming coining. The result. This sneaky attack lets the adversary break the secret key with a low number of traces, undermining the very protection the signature attenuation was built for. Classic, isn't it? Can't get through the front door. Trick the guards into thinking everything's fine while you subtly weaken the foundations.
It really does sound like digital chess, much more subtle than just trying keys. It's exploiting how the countermeasure itself works, tricking it into lowering its guard. Given how precise this voltage drop needs to be, how sophisticated does an attacker need to be? Is this state-sponsored stuff, or could a hobbyist do it?
That's a great question, and it really underscores the escalating threat level. This isn't something you do with off-the-shelf kit in your basement. Pulling off a malicious voltage drop attack requires serious sophistication. You need extremely precise control over the chip's power delivery, often specialized equipment that can inject very controlled voltage changes. Plus, you need a deep understanding of the specific hardware implementation. You need to know which voltage levels push the CS into the linear region without crashing the whole chip. That often implies access to detailed schematics or at least significant reverse engineering effort. So, while maybe not exclusively state actors, it's definitely in the realm of well-funded, highly skilled adversaries. Think organized crime, corporate espionage, maybe advanced research labs. The cost and expertise put it beyond casual hackers. But there's also a fine line for the attacker too. Lowering VDD by a significant amount will cause the SMC loop failing to supply the AES current, and hence the crypto itself will not work, failing the attack. So it's not smash and grab, it's surgical. They have to operate in this very narrow voltage window to succeed without just crashing the target and giving the game away.
Okay, so you've got this amazing countermeasure, the IDCSAs, attenuating the whispers. But then a smart attacker finds this sneaky workaround, manipulating the power itself.
Right.
What do you do then? How do you even defend against such a subtle, almost invisible manipulation?
That's the million-dollar question, right? And it's where the intelligent part of IDCSA really earns its name. To boost security further, and crucially, ensure the countermeasure's sustainability against this malicious voltage drop attack, they implemented an intelligent attack detector circuit. This transforms the IDCSC from just a strong defense into a truly self-aware, active guardian. Its main job, it's proactive. It's designed to output an alarm to stop the operation of the encryption engine if it senses the CS, current source, goes out of saturation region, which, as we just discussed, is the dead giveaway for this specific voltage drop attack. But it doesn't just stop things. It can also activate other higher power countermeasures intermittently. So it doesn't just hit the brakes. It can escalate defenses, maybe turn on more robust, but power-hungry measures only when it detects an attack, making the system adaptive. And what's really elegant, really efficient design-wise, is that it leverages existing parts. The bleed RO, the ring oscillator we mentioned earlier, the one used for local feedback and input to the global loop. It's also leveraged in the intelligent malicious voltage drop attack detector block. Smart engineering, right? Using shared hardware for multiple security functions. Reduces complexity, power use, chip area. So how does this detector actually work? It uses two key things. That bleed RO and a second replica RO driven from a voltage divider from VDD. This replica RO is carefully designed to match the voltage right at the AES engine's internal supply node, VAES. Now, ring oscillators, their oscillation frequency is super sensitive to the voltage they receive. If the main voltage, VDD, drops maliciously, but the internal VAS is held more stable by the system, the frequencies of these two ROs, the bleed RO and the replica, will drift apart in a very specific detectable way. The count from both the ROs are fed to a digital comparator. This comparator constantly watches the frequencies, compares them. Based on that comparison, it decides if the CS is out of saturation, detecting a malicious voltage drop. If it detects the attack, it subsequently alarms the encryption engine to turn off or triggers those backup countermeasures, and it does this fast. And this Smart Guardian, it doesn't cost much in terms of chip resources. The detector's area is just 0.008 millimeter two. That's tiny, less than 6% of the AES core size. A small footprint for critical security. Even better, the sample waveform in the paper shows a detection latency of less than 1 millisecond. That's basically instantaneous in chip time. The attack gets detected almost the moment it starts, long before any significant information can leak out.
That is genuinely fascinating. It's not just passive anymore. It's active, adaptive, constantly monitoring its own health, specifically looking for signs of subtle manipulation. It's like a vault sensor that doesn't just detect drilling, but also detects if someone's trying to subtly freeze the lock mechanism and then immediately slams everything shut, calls for backup, maybe deploys countermeasures. A proactive, intelligent guardian, and that sub-millisecond detection. Incredible speed. Okay, so with such a clever, multi-layered design, the attenuation, the intelligent detector, the big question is always, does it actually work? How well? The researchers put their IDC SASE through rigorous testing, and the results, well, they seem pretty compelling, actually quite reassuring.
Oh, the data in the paper paints a very clear picture. It's undeniably effective. First, let's look at the baseline again for comparison. An unprotected AES circuit, no countermeasures. Using CPA, the MTD minimum traces to disclosure was just 2.3K traces, 2,300. Using SEMA, the EM attack, it was 4.4K traces. These numbers are extremely low. An attacker could break this very easily, very quickly, with standard gear. Now compare that to the IDCC, running normally without the malicious voltage drop attack. The results, just astounding. Both SEMA were unable to recover the key until 200 MB traces, 200 million traces, both in time and frequency domains. That's a colossal improvement. Makes key extraction practically impossible for most attackers. Gathering 200 million clean traces, that's a monumental task, often prohibitively expensive and time-consuming. They also ran a test vector leakage assessment, TVLA.
Right, TVLA. What exactly is that again? How does that test work?
TVLA, Test Vector Leakage Assessment. Think of it as a gold standard health check for a crypto chip's leakiness. It's a statistical method designed to sniff out any information leakage, however subtle. You feed the chips specific inputs, test vectors. Some depend on the secret key, some don't. Then you collect side channel traces for both sets. If there's a statistically significant difference in the traces, power, EM, between the key-dependent data and the key-independent data, that's a big red flag it's leaking. The t-value measures how strong that difference is. Over 4.5 usually means meaningful leakage. The TVLA on the IDC-SC showed that getting a meaningful leakage t-value 4.5 requires 500,000x more traces compared to the unprotected counterpart. That's an incredibly strong result, a widely recognized sign of exceptional robustness against side-channel snooping. Okay, but what about that clever malicious voltage drop attack? They tested that specific scenario too, very thoroughly. With the IDCCC running, and this is key for the test with the detector turned off, just to prove the attack works if undetected. In that case, CPA reveals the correct key byte with 105K traces. Now, 105,000 traces is way better than the unprotected 2.3K, but it's still much lower than protected IDC SAS AES 200M when it's fully working. So this absolutely confirms, yes, the malicious voltage drop attack does work against the attenuation hardware if it's not detected. And this is precisely where the intelligent detector proves its immense value. When the full IDC SAC with intelligent malicious voltage drop detector was active, the timing measurements confirmed that incredible detection latency, less than 1 meters. In that tiny, tiny window, before any real leakage can happen, the system would either shut down or switch to those stronger countermeasures. Essentially, any SEMA attack is impossible because the threat is neutralized almost instantly. The moment the attacker tries to subtly tweak the power, bam, the digital door slams shut. No key leakage. Finally, the paper compares their work directly with existing state-of-the-art countermeasures. It explicitly highlights. Our countermeasure for the first time includes an intelligent attack detector for this specific kind of power delivery system manipulation-based intelligent attack. That makes it genuinely pioneering work. Furthermore, using only a single digital-friendly cascoding technique without RO bleed randomization, IDCC achieves the highest MTD by any digital signature attenuation. 20M is a 200 run at 10x over SOFL. It also achieves the highest power TVLA improvement with respect to unprotected counterpart. And the cherry on top, its flexibility. It can also be cascaded to any other generic countermeasure for higher security, making it a powerful, versatile building block for future secure designs.
It really is clear. This IDCS isn't just robust against the usual attacks. It anticipates and actively counters these new, super sophisticated vectors that target the defenses themselves. It's not just a stronger lock. It's a lock that screams for help, locks everything down, maybe even deploys extra defenses if someone tries to pick it too cleverly or subtly. It really embodies this adaptive, proactive security mindset, always trying to stay one step ahead in this relentless digital arms race. Hashtag, tag, tag, broader implications and the unseen battlefield.
Yeah, and we zoom out, connect this to the bigger picture. This research really throws a spotlight on the ongoing high-stakes battle in hardware security. It's this constant arms race where just having strong algorithms isn't enough anymore. You have to rigorously anticipate how attackers will exploit the physical implementation, right down to the electrons in the silicon. This paper shows a crucial shift, doesn't it, towards active defense, not just passive, at the silicon level, giving the gate sentience almost, the ability to fight back. And one of the biggest broader implications is its generic applicability, the fact that it's digital friendly and, importantly, can be cascaded to any other generic countermeasure. That means its impact could go way beyond just AES 256. It offers this versatile, strong building block for all sorts of crypto implementations, maybe even other sensitive circuits needing side channel protection. That flexibility is vital for getting it widely adopted, for future-proofing designs against threats we haven't even seen yet. It also really pushes the envelope for what we call adaptive security systems,
where the defense isn't static. It intelligently reacts to threats it detects. This proactive approach is becoming absolutely critical as adversaries keep developing new, unexpected attack methods. The future of security. It definitely involves more self-aware, self-defending hardware. Hardware that knows when its basic operating conditions are being messed with and responds dynamically. Of course, that raises new challenges too, right? Making the detector itself tamper-proof, avoiding false alarms, managing the complexity. But that's where the field is heading. And of course, designing real chips always involves practical design trade-offs. The paper is good about providing the specs which engineers need. It's built on a 65mm CMSLP, low-power process, common tech. The basic AES core itself is efficient. 0.8 V28000 MHz 275 UW. A pretty good performance. But adding the IGCSE does have overheads. The area of overhead extra chip space is 35%. The power overhead extra energy use is 50%. Interestingly, the performance overhead is 0%. It doesn't slow down the actual encryption. But those area and power costs are real. 35% more area could mean higher manufacturing costs per chip. 50% more power could mean shorter battery life. These are the tough trade-offs product designers have to weigh when deciding if they need this level of security in their next gadget.
It's a fantastic piece of work, really a testament to the idea that in cybersecurity, especially down at the hardware level, the game of cat and mouse just never stops. It's this relentless innovation race. Every new defense eventually inspires a new attack, and every new attack demands an even smarter, more agile defense. An unseen battlefield fought with electrons and algorithms, but with huge implications for all of our digital security. It's pretty amazing engineering, really. Hashtag outro. So what does all this mean for you, our listener, in your day-to-day digital life? Well, it means that behind the scenes, brilliant engineers are constantly working to refine those digital fortresses, protecting our data, our privacy, our critical systems. They're not just making them stronger with harder math, they're making them smarter, more aware of their physical surroundings, and crucially, able to detect even these incredibly subtle, intelligent attacks that exploit the physics of computing itself.
Yeah, this deep dive really shows that true security isn't simple. It's multi-layered, it's dynamic, it stretches all the way from abstract math through algorithms, right down to the microscopic details of circuits and those faint electrical whispers in the silicon. It definitely forces us all to question our assumptions about where the real vulnerabilities lie and to appreciate the sheer ingenuity needed to protect our increasingly digital world.
And that brings us to a final provocative thought for you to maybe mull over. As our digital lives get ever more tangled up with physical hardware chips in your smart home, massive servers in the cloud, everything in between, where do you think the next critical frontier of cyber defense will emerge? Will it be deeper in the code, or maybe right down in the physics, the electrons themselves, or perhaps somewhere entirely new, blending both in ways we haven't imagined yet? That's all for this deep dive into the fascinating and incredibly important world of hardware-level cybersecurity. We hope you feel a little more informed and maybe just a little more amazed by the intricate, unseen battles being fought constantly on your behalf.